This tutorial is going to show you how to test the assumptions of a binary logistic regression on R. So what are the assumptions? Firstly, that the dependent variable is binary. So this means it will be coded as something like 1 or 0 or yes or no. The data should be independent and not paired. The independent variables should not correlate too strongly with each other. Any independent continuous variables should be linearly correlated to the log odds of the dependent variable. And finally, there should be no outliers in your data. In this tutorial, we're going to use the Titanic train dataset, which can be found in the Titanic package. We will also be using the GG2 package later on. So the first thing that we need to do is install and load these packages using the following code. Remember that you have to install an R package once, and then your R environment will remember it forever. But each time you want to use it, you need to load it in using the library function. So in this tutorial, we'll be looking at what independent variables predict whether a person survived or not on the Titanic ship. So the following independent variables will be used: age, fare, class, and the dependent variable will be survived. So to check the first two assumptions, which are that the dependent variable is binary and that the data are independent, you can just do this by looking at the data. On R, you can view the Titanic train dataset by using the view function. Remember that view has a capital V. So this is what the data looks like. Here is our dependent variable, survived, which as you can see is coded as 1 and 0. And here you can see each row represents an individual data point, so our first two assumptions are met. Next, we will check that the independent variables do not correlate too strongly with one another. In R, you can do this by using the core test function. Before running the correlations, though, we need to remove any missing data, as R likes your variables to be equal in length. To do this, we will create a new dataset called data and write the following code to get rid of all the NAs which are missing data in the dataset. Now we are ready to run the correlations. Remember that Pearson's correlations are used for continuous variables, so for example age, and Spearman's correlations are used when you have ordinal variables. So for example, our class variable is coded as 1 equals first class, 2 equals second class, and 3 equals third class. And you can do the correlations on R using the following code. Some things to note about this code is that data is the new data set we created using the code above, which has removed all our missing values. The $sign accesses all the variables in the data set, and the method is what type of correlation you want to use. So here we have correlated all our variables with each other. And here are our results. As a rule of thumb, anything above 0.7 would be too highly correlated. As you can see, one correlation is majorly above 0.7, and that is between age and fare. This means that ideally we should only have one of these in our model, but you can test these items separately. Please remember though to check if your supervisor has different cutoff points. Next, we need to check that the continuous variables, which are age and fare, are linearly correlated against the log odds of the dependent variable. And an easy way to do this is to create scatter plots using the following code. Remember that you need to have the ggplot2 package installed and loaded to be able to use this code. To do this, you need to firstly run the logistic regression model, then make a probabilities and logic variable, as I have done here, before making the plots. Please note that there are other methods to check this assumption, such as using the box-tidwell test. And here are our graphs. So as you can see, both of our continuous variables appear to have a fairly linear relationship with the log odds of the dependent variable. And finally, we need to check that there are no outliers. Again, there are a number of different methods to do this, and one is looking at the Cook's distance value. So to use the Cook's distance value, you can use this code. And this code will produce a graph of all observations and the Cook's distance value. Here we have highlighted the top 6, which are potentially our extreme values. If you find that you have outliers in your data, in some cases it may be best to remove the entire data point, but if there are several, then it may be best to transform the data. Finally, here is the copy of a code that I use to check all of the assumptions. And you can edit this to represent your own data when running your own binary logistics regressions. And some things to remember are: install and load any packages at the beginning that you may need, otherwise you might run into an error. Remove any missing data, as sometimes R will give you an error as it likes things to be in an equal length. There are often multiple ways of doing these things. These are just some examples. And finally, always check with your supervisor for specific cutoffs of methods that they want you to use.